This is a lesson on the definition of pressure in the Fluid Statics and Dynamics unit. Let's begin looking at fluids from the perspective of forces and how to quantify the effect of a force on a fluid. When we think about fluids on a microscopic level, they're actually molecules bouncing around in a container. Okay, and so those molecules, as you can see in the diagram, will hit the side of the container. And overall, the forces in the horizontal direction will cancel out, but you get this outward force perpendicular to the surface, and that's what we think of as pressure. When you think about blowing up a balloon, the pressure is perpendicularly normally pointed from the surface of that balloon outward. All of the horizontal forces along that surface cancel each other out. So we can look at only a vertical force perpendicular on an area. So that brings us to our definition of pressure. Pressure is the force per unit area over which a force is applied. And you can see in the diagram here that we have a surface. There's a force being applied to that surface, and there's an area over which that force is being applied onto that surface. And so pressure is defined as force over area, F over A. This is a scalar quantity. Pressure does not have direction, it's just a quantity. And the units of it is force per unit area, newtons per meter squared, and that is a unit of Pascal, newtons per meter squared. There are other units of pressure. There's the British versus the metric, but then there's other types of pressure, other normals or standardizations of pressure that are used in different contexts. So for instance, for tires, if you're in America, pounds per square inch is how you would measure a pressure in the tire, like 30 pounds per square inch, 35 pounds per square inch. If you have a bicycle tire, it's like 60 or 65 psi. And there's the conversion factor from psi's to pascals. Atmospheric pressure is also a standardization. 1 atmosphere, if you are at the surface of the planet at sea level, there's 1 atmosphere of air above you, and that exerts a pressure down. And we call that 1 atmosphere. At surface, at sea level, on the planet Earth, there is 1 atmosphere of pressure. That's actually equal to 1.013 times 10 to the 5th pascals, or interestingly enough, about 15 psi. So there's some conversion factors there if you wanted to convert. There's millimeters of mercury. A barometer works by measuring a column of mercury. And so that column is measured in the height of millimeters. And so when you see millimeters of mercury, that's what it's talking about here, millimeters of mercury. And 1 millimeter of mercury is 133 pascals, not a lot. And 760 millimeters of mercury is 1 atmosphere. Okay. Bars is another. You might see this more in weather. 1.013 bars is 1 atmosphere, or 10 to the 5th of that pascals. In some contexts, you will be asked to know the difference between gauge pressure and absolute pressure. Gauge pressure is the pressure relative to atmospheric pressure. So everywhere along the surface of the planet, there's 1 atmosphere of pressure. And so gauge pressure does not include that pressure. It's just what's the relative additional pressure. It will be positive for when the gauge pressure is greater than 1 atmosphere, and it will be negative for when the gauge pressure is less than 1 atmosphere, because it's relative. If it's less than 1 atmosphere, it's negative. If it's greater than 1 atmosphere, it's positive. So a negative 0.2 atms would mean that the absolute pressure is 0.8 atms. It's the pressure at the surface of the planet minus that relative pressure, which is 0.2 atms, and that's how you get 0.8 atms. So you see that absolute pressure, the absolute pressure with all the pressures involved, the absolute pressure is going to be whatever that gauge pressure is plus whatever the atmospheric pressure is at that point on the planet. This is true for other planets too. If you're exploring space, for instance, you may see this on other planets. The first example I picked out is the phonograph needle. The pressure exerted by a phonograph needle on a record is surprisingly large. If the equivalent of 1 gram is supported by the needle and the tip of the needle is a circle with a radius of 0.2 millimeters, what pressure is exerted on the record? Okay, so we're taking 1 gram and we're distributing it over 0.2 millimeters in radius. So 0.2 millimeters. So if you think about a millimeters like that and you want a fifth of it, so it's teeny, teeny, tiny. So I'm going to write down here the radius. The radius of the area that we're going to be looking at is 0.2 times 10 to the negative third meters. I'm going to go ahead and convert that to meters right away. The area that I'm looking at, and we can think about the needle touching down onto the surface, all right? So it's a circle of radius r, and the force that this is applying is 1 gram, right? There's a force of gravity, which we know is mg, and that will be the mass here, 1 gram times gravity. So I'll write out the equation for pressure, P equals force over area. The force is going to be mg, and the area is going to be pi r squared. I'm ready to plug in numbers. M is 0.001 kilograms. Remember, I want this in SI units to plug into here to get pascals out. So 0.001 times a factor of gravity, 9.8, divide by pi times the r squared. So I'll put in 0.2 times 10 to the negative third quantity squared. And when you run this through your calculator, this is the pressure you're going to get. And they say it's large, right? It's surprisingly large. So when we calculate this, this is 7,798.5.99 newtons per meter squared, right? We had a force up top and an area on the bottom. So that's in pascals. So if you want to, you could in here write pascals. Let's see how large it is. They say it's large. So this is, if I convert this to atmospheres, I'm going to know that there is 1.013 times 10 to the fifth pascals in 1 atmosphere. And so when I convert this to atmospheres, I get 0.7699 atmospheres. So a little over 3/4 of an atmosphere there. On that teeny tiny surface between the needle and the phonograph, right there, that's pretty large. When we figure out how many psi this is, 1 atmosphere is 14.7 psi. This equates to 11.3 psi, which is pretty substantial. It is surprisingly large for such a small surface and a small mass. The second problem I picked out to exemplify pressure is the swimmer's hand. Suppose that the pressure acting on the back of a swimmer's hand is 1.2 times 10 to the fifth pascals, a realistic value near the bottom of a diving end of a pool. The surface area of the back of the hand is 8.4 times 10 to the negative third meters squared. Okay. Determine the magnitude and direction of the force acting on it. So if you have your hand underwater at the bottom of the pool under a diving board, that's how much pressure that's going to be on top of your hand. Okay. So when I look at this, I'm like, okay, this is a pretty high pressure. This includes the atmospheric pressure. So we're looking at the case of the absolute pressure, where the absolute pressure equals the gauge pressure plus the pressure of 1 atmosphere. So when I look at gauge pressure in here, 1 atmosphere, I know this has to be 1 atmosphere, which I can convert to pascals, no problem. The other component of this is going to be the gauge pressure, the relative pressure underneath the surface of the water, where that hand is, right? Here's the surface of the water. There's 1 atmosphere pressure out here, and then there's an additional amount of pressure due to being under the water, which is in the next lesson. We'll figure out how to calculate this. But down at the bottom here where the hand is, and let me do a hand here, there's an additional pressure due to the water. So that's what the gauge pressure is, this additional pressure after the 1 atmosphere, in addition to the 1 atmosphere, there's this gauge pressure due to the liquid on top of the hand. And so if I want to know the force on the hand due to the water, right? There's a force on the hand due to the water that will be related to this gauge pressure. So I'm going to solve this equation for gauge pressure. Gauge pressure equals the absolute pressure minus 1 atmosphere pressure. So the absolute pressure, which they tell us in the problem, is 1.2 times 10 to the 5th pascals. Then I'm going to subtract off 1 atmosphere pressure, right? 1 atmosphere pressure is 1.013 times 10 to the 5th pascals. So I'm seeing that gauge pressure is 0.187 times 10 to the 5th pascals. You can reduce this to a different scientific notation or what you like there, but I'm going to leave it like this for now because I'm not really interested in this number. What they've asked me for is determine the magnitude and direction of the force acting on the hand. Well, they give me the area of the hand, and I know pressure equals force over area. Area equals 8.4 times 10 to the negative 3rd meters squared, and I found the pressure, and they're asking me to find the force. So when I solve that equation for force, I'm going to get pressure times area. So the pressure is 0.187 times 10 to the 5th pascals. I'm going to multiply it by the area, 8.4 times 10 to the negative 3rd meters squared. And when I multiply that through in my calculator, run it through my calculator, I get 157.1 newtons, which seems reasonable when I think about how many pounds that might be. If I divide this by 9.8, that would say that a mass of about 16 kilograms is sitting on top of that hand. That's about what's on top of that hand, a mass of water.